let's take a look at some of the properties of inverse matrices, okay? So we're assuming we have square matrices of appropriate sizes. So that means they're square and they're all the same sizes so that you can multiply them together, okay? And let's prove each one of these. So our first is that the inverse of the identity matrix is just the identity matrix. All right. Now, to prove this, and in fact, to prove all of these, we are going to use the definition of what it means to be an inverse. Okay. A and B are inverses. Two matrices are inverses if when I multiply them or multiply them in either direction, I just get the identity matrix back. If this happens, then my matrices are inverses. Right? So observe that if I multiply the identity matrix by the identity matrix, I get the identity matrix. This is just like if I multiply 1 times 1, I just get 1, right? Any number times 1 is itself, so when I multiply 1 times 1, I get 1. Similarly, any matrix times the identity matrix is itself. So if I multiply this matrix by the identity matrix, I just get this matrix back. But since I got the identity matrix, that must mean that these two are inverses. Okay? B, for an invertible matrix A, the inverse of the inverse of A is just A. All right? So observe A times A inverse. Write it this way. A inverse. Well, A times A inverse is just the identity matrix by definition. Right? That's what it means for this to be the inverse of A. If I multiply them together, I get the identity matrix. But when I multiply two matrices together, it doesn't matter the order, right? So it also means that this has to be the inverse of that. Okay, so the inverse of the inverse is just matrix A. Okay? All it means to be an inverse is that if I take the two matrices and multiply them together, I get the identity matrix. That's what's happening here. And so A must be the inverse of this matrix. So it must be the inverse of the inverse. All right. C is maybe the most interesting result here. If A and B are invertible matrices, then the product matrix is also invertible. If I multiply the matrices, it's also invertible. And the inverse of the product is the product of the inverses, but with the multiplication order reverse. This is called the shoes and socks rule because it's similar to how you put on and take off your shoes and socks. How do you put on your shoes and socks? Well, you put on your sock first, then you put on your shoe, right? Now, invert it, undo it. How do you remove your shoes and socks? First, you take off the shoe, and then you take off the sock. It's in reverse order, right? Putting them on, the sock goes first, then the shoe. Taking them off, the shoe has to go first, then the sock. It's the same thing with matrices, okay? And that's why the order flips. So let's prove it. Observe. So all I'm going to do is I'm going to take B inverse A inverse, and I'm going to multiply it by matrix AB. Right? And if this is the identity matrix, then I have my answer. Well, I know A inverse times A is the identity matrix. So I get B inverse times the identity matrix times B. And any matrix times the identity matrix is itself, so I times B is just B. And B inverse times B is just the identity matrix. Okay? And so when I multiply these, I get the identity matrix, which means these must be inverses since we know they're both square matrices. Thus, the inverse of the product matrix, AB, is B inverse times A inverse. Okay? Let's do D. We're going to prove it the same way. For D, if A is an invertible matrix and K is a non-zero number, that's important, the non-zero part, then the inverse of the scalar multiple of A, K times A, is 1 over K times the inverse of matrix A. Okay, so again, to prove their inverses, because they're square matrices, all I have to do is show that when I multiply them together, I get the identity matrix. All right, so I'm going to take K times matrix A, and I'm going to multiply it by 1 over K times A inverse. Okay, now remember when we multiply matrices, the scalar matrix multiplication, it's associative, so I can move all the scalars to the front. In fact, let me do it this way. Okay, so K times 1 over K, that's 1 because they're scalars. These are just real numbers. And then A times A inverse, that is the identity matrix. And then 1 times the identity matrix is just the identity matrix. If I multiply any matrix by scalar 1, it just keeps the matrix the same. Right? So because it is equal to the identity, the inverse of Ka is 1 over K A inverse. All right, one more, and this one's a little interesting. If A is an invertible matrix, then the transpose of A is also invertible, and the inverse of the transpose is the transpose of the inverse. Okay? So again, I'm just going to multiply them together. So A transpose is the matrix we're saying has an inverse, and we're saying that inverse is maybe a double set of parentheses here. Actually, you know what? No, let's do one set less. A inverse transpose. Okay? Now, to deal with this, I notice I have matrix multiplication. So what I'm going to do is I'm going to use one of the properties of the transpose. If I have two matrices and I'm transposing them, what I get is the second transpose, then the first transpose. Okay, so I'm going to go ahead and use this property, but I'm using it in reversed. I have something that looks like this, two matrices that are transposed multiplying each other. I want to turn it into something like this, two matrices that are multiplying each other, and then you transpose. So if I do that, I'm going to swap the order. So A inverse comes first, then I transpose. Okay, and now inside these parentheses, A inverse times A is just the identity matrix. And the identity matrix is a symmetric matrix, which means when we take the transpose, we just get the identity matrix back. Which means these two matrices have to be inverse. So the inverse of A transpose has to be equal to the transpose of A inverse.